All right, welcome back. At this point, we've taken a deep dive on evaluating these definite integrals using this limit sum definition. I want to dig a little bit deeper on a concept that I spoke about in the last video, specifically getting positive and negative values out for these definite integrals. So first, I want to show you this. This is a function f of x equals x cubed minus 11x squared plus 24x. And what I'm looking to do is to evaluate the definite integrals from 0 to 3, from 3 to 8, and then 0 to 8 right here. There are a couple important properties that are included here, but I specifically, again, want to dig in on when will we output a negative for our definite integral and why. Okay, with this function f of x, importantly to this conversation is that we have three zeros. Here at 0, we're at 0. We're 0 at 3, and we're 0 at 8 right here. And so these are the boundary points that I'm going to use to evaluate these integrals. I'm also not going to show the work. We could do the work of actually evaluating these with the limit sum, but that's a lot of extra work, and I have done it previously, so I just don't want to deal with that part. I just want to give you these values and talk about these with relations to area. First and foremost, the integral from 0 to 3 of this function, which is computing the area under the curve right here, that ends up being 29.25. There's nothing too interesting there. I guess you just got to take my word for it. You could do the work of evaluating that, but I spent some time to make sure that was accurate. Next, I want to talk about this integral. So now I'm going to integrate this function between 3 and 8. Now, in this case, because this curve lies under the x-axis, this will end up being negative. And it ends up being negative 114.58. And this is the important part of the conversation that I want to talk about right now. We developed this idea of a definite integral by taking these non-negative functions and looking at the areas under the curve. Specifically, what we're doing in all of these cases, and you know this, is that we're creating these small little rectangles that have this small width and take the function value as the height. So importantly, at every x value, we're taking the function value and multiplying it by this difference. Well, when the function value is positive above the y-axis, then this is going to result in a positive value. But in the case when our function values are negative down here, the height, quote unquote, of this rectangle is actually going to be a negative value. So we'll get a negative function value times this positive change in the interval, which will output negative. So any point when our graph is below the x-axis, these outputs, the output of the definite integral will be negative. And here's the important connection with all of this and part C right here. If we're now going to integrate between 0 and 8, what will happen is as we integrate on this interval between 0 and 3, we're going to get positive sums out on each of these steps because of the positive function values. And then after that, we're going to get these negative function values. But importantly, if we integrate from this whole path from 0 to 8, it's going to be the interaction between this positive area and the negative area. So in fact, from 0 to 8, that integral would just simply be the addition of these two areas. Obviously, this negative is larger and would win the battle, but this becomes negative 85.33. And so the really important takeaway from this is two parts. Is if you're doing an area argument, which we're going to do in a couple examples right after this, any areas above the x-axis are considered positive definite integral values. Any of the areas below the y-axis are negative integral values. And if we're integrating on a span that includes positive and negative integral values, we need to evaluate those areas separately and then put the information together. All right, in this first example, we're being asked to evaluate this integral value, not using the Riemann sum, the limit sum definition of the integral, but instead using an argument area, which can be much easier if you can understand what this object looks like graphically. In this case right here, we have the square root of 16 minus x squared. If right out the gates you don't understand or know what this is, what we could do is play with this a little bit. We set this equal to y in this case, so y equals the square root of 16 minus x squared. And then I'll square both sides here to get rid of this square root to get y squared equals 16 minus x squared. Finally, I'm going to add over this x squared term, and I see that this is actually a circle. But specifically, this equation is a circle, and this is simply the top half of that circle. And I'll sketch this real fast to hopefully remind you of this property. So x squared plus y squared equals 16 is a circle centered at 0 with a radius of 4. And the radius always comes from the square root of this constant value right here. We know it's centered at 0 because there's no transformations done between these x and y terms. Specifically speaking though, and this is important moving forward, is that while the whole circle is this, the top half of this is defined with this equation right here. And the bottom half would be defined with this equation right here. And this is important because in this form, as necessary with the integrals, this is written in function notation. A circle is not a function because it does not pass the vertical line test. For many of the inputs, there are more than one output, right? So if we split the circle into two functions, this would be the top half and this would be the bottom half. Specifically though, we're interested in this, and what we want to do is to compute the area, because the area of this circle right here is equal to this integral. And again, we're integrating between -4 and 4, which is perfect. It lies right on the boundaries here of our circle. So our job is to figure out what the area of this half circle is, which is not very difficult. We know that the area of a circle is pi r squared. And so if we want to find the area of this, it actually would be 1/2 this area. So the area in this case would be 1/2 the area of the entire circle. And in this case, our radius is 4. So we can compute this by plugging in 4 here to get 1/2 times 4 squared is 16. This ends up being 8 pi. Again, I did that fairly quick at the end just because I'm dealing with the equation of the area of a circle, which I know you've all seen many, many times. But again, the argument was, okay, if I'm going to use an area argument to find this definite integral, the definite integral is equivalent, as long as I have a non-negative function, to the idea of area. Once you understand what geometric object you're working with, finding the area of that, and then in this case, I had to divide it by 2 because I only have half of this circle. I don't have the other half. And this will give me 8 pi as the value of this definite integral. This is a fun thing to talk about right now too, because in a couple of weeks, what we're going to be doing is these trig substitutions. And what's going to happen is when we actually evaluate algebraically this kind of integral, we're going to introduce trig functions, which is where we end up getting out this 8 pi value. All right, in our second example, we're being asked to evaluate the integral of 2x minus 4 from -2 to 5. Again, what I'm going to employ is this argument of area. Importantly to this conversation that was not in the previous conversation is we need to deal with these negative and positive area values that we talked about at the beginning of this video. So first and foremost, let's sketch a graph of this. This is simply a linear equation, so it's a lot easier to get the graph here. This has a y-intercept of -4, so it starts right here. It has a slope of 2, which would mean we need to go up over twice to get to our x-intercept. So right here we'll call this 2 right here is our intercept. And then let's get our endpoints here. So that's 1, 2, 3, 4, 5, and then we're at to -2 here. What I'm just going to do now is get my endpoint. So if I plug in a 5 here, I have 10 minus 4, which is 6. So this point right here is 5, 6. And then at -2, if I plug that into my function, I get -4 minus 4 is -8. So at -2 here, let's make this look somewhat to scale. This is -2, -8 is that point. And everything seems to line up pretty good. It's supposed to be a straight line, right? But I'm kind of sketching this freehand. Let's just make this look pretty for right now. All right, in this case, we don't have an obvious shape, right? Like last time we had this obvious circle when we graphed this, and this we just have this straight line. But what I'm going to do is employ this, what I talked about at the beginning of the video. I'm going to focus first of all on this 0. So we have this 0 at x equals 2. And what I'm going to do is to break up the areas under the curve here, or between the curve and the x-axis, to the positive and the negative part. Specifically, I'm going to attack this area right here between 2 and 5, and separately attack this area between -2 and 2. So this area under the curve right here is going to be a second area. And hopefully it's clear why I'm doing that. Again, because this area of this object right here, it will be negative. And after 2, this area will be positive in terms of the definite integral. They're both positive areas, but when evaluating with the definite integral, this is negative and this is positive because this has negative function values and this has positive function values. Beautifully, in both these cases, we just have rectangles, and so we can simply calculate these with the area equals 1/2 base times height. This distance right here from 2 to 5 is a width of 3, or the base of 3. This has a height of 6 right here. And then for this rectangle, this measure is 8. And this measure from -2 to 2 is 4. And so I'll calculate both of these areas. This area here is 1/2 times 3 times 6. 3 times 6 is 18 times 1/2 is, this gives me an area of 9. Over here in this area, I have the area is 1/2 4 times 8. 8 times 4 is 32, times 1/2 is 16. So then putting that all together, I've evaluated this integral from -2 to 5 of 2x minus 4 by evaluating these two separate areas. What I have is an area of positive 9 and an area of -16, or I'll just write that as -16. This gives me that the value of this definite integral from -2 to 5 would be -7. Again, to me, this is beautifully interesting, but if instead of using this argument, we attacked this with this limit sum definition and did all of that work with the Riemann sums, we would get out this same value. This is just a beautifully simple way of doing this, and whenever you can, or when asked, creating a picture, finding the geometric shapes and they're finding the areas, always remembering areas above the x-axis are positive integral values, areas below the axis are negative integral values. And what's important to that are finding the zeros of the functions on that interval, because that's where you're going to have to break up your arguments or your investigation of the areas. All right, let's now get down some properties of integrals that will make our lives a lot easier moving forward. Most of these are really straight and obvious once you understand the concept of the definite integral, but I'll defend them a little bit as I move forward. First of all, we're taking the definite integral from a to b of a constant function. In this case, we know that this will evaluate to c times b minus a. Now, that might not be obvious just by looking at it, but let's think about what this is. So a constant function is not that interesting. We'll choose to visualize a positive constant here. It works for both positive or negative. So we have this function that is the same value no matter what. We're looking at an interval a to b here, and this integral is going to calculate the area under this curve between these two. But as you may see it already, this is simply a rectangle. It's a rectangle with the height of c, because that's the value of this constant function, and has a width here of b minus a, or the width of that interval. The area is c times b minus a. All right, these next two properties I really get for free because they're both properties of limits and summations. And never forget, this definite integral is simply this limit sum. So if we have properties that work for both limits and summations, they have to work for the definite integral. In this case right here, for the first one is this idea of a constant times this variable function. We can factor out that constant outside of the definite integral so that when we actually do the work of computing the integral, it's not in the way. And again, don't think too deeply about this, but it means if you have something like 5 times x squared, you can ignore the 5 as you actually integrate the x squared. Next up is this property where I'm integrating, in this case, with an expression that has multiple terms. And when I do that, just like with the limits, I can split that up and attack each term separately. So in this case right here, I can split this into the integral from a to b of f of x dx plus the integral from a to b of gx. By the way, I'm not going to write the property for subtraction, but if a property like this works for addition, it has to work for subtraction. I'm sure you know that. The textbooks often will list both. I don't see a reason to, because the definition of subtraction is adding the opposite. So if subtraction is addition, why write a property separately for both addition and subtraction? I digress. Let's move on to the next property. Our fourth property here is really straightforward. This is the integral from a to a of f of x. So we're trying to find the area of this under this curve of this interval that has 0 length. It should be obvious that this will be 0 because this is a straight line with no width. And this actually has some implications in proofs moving forward. So we want to have this in our books, but you won't see this really very often. All right, property number 5 is pretty cool. In this case, we're allowed to swap these boundary points for our intervals. So I can swap a and b, and it might be hard to conceptualize why we would do that at this point, but you'll see moving forward. If we swap those two numbers and integrate, in this case, we aren't going to get the same value, but we're going to get the opposite out. Now, again, you might be thinking, how is it making any sense to go integrate this way, or why is it negative? And the important thing that you can understand here is this delta x that we've defined in this summation is defined as b minus a over n. Meaning this value in both these cases will be exactly the same in each of those summations. The difference is that if we swap a and b, this delta x will be negative or it'll be the opposite of itself when you switch these around. And so the only change when you swap these boundary points is the value will be a change from a negative to a positive or positive to a negative. All right, and for number 6, what we get is the addition of two different integrals equals this last definite integral. In this case right here, if you integrate from a to b on a function, and then from b to c, that when you add those to get those integrals together, you're going to get the integral from a to c. And the proof of this is pretty straightforward. It's what I did in the beginning of this video. If you remember, I was looking at this cubic function from 0 to 8, and I argued that what I would do is I would look from 0 to 3 first. 3 would be this b value, right? So from 0 to 3, I calculated that area, and then I calculated it from 3 to 8, the c value, and the addition of those two areas together would give me the value of the integral from the whole length from 0 to 8 or from a to c. When you're working with this in real life, the important part about this formula to kind of justify in your brain is this b. Find where these are the same and your life will be a lot easier and you'll be able to develop these. Generally speaking, we always think about b lying between a and c, but it's actually this formula works even if b does not lie between them. So again, I think a goes to b, then b goes to c. That covers all from a to c. Number 7 here is pretty straightforward. It's what you'd expect. If you have a function that's greater than another function on an interval, then if you integrate each of those functions separately on that interval, the integral with respect to f of x is going to be greater than the integral of g of x. And again, this should make sense if you understand this idea of integration. If these have larger values on the entire interval, then the integral will be larger than the other, or g of x in this case. And again, this is a property that you're not going to use a ton and should be fairly obvious, but this will be really useful in helping us prove properties moving forward that will make our lives easier when evaluating these integrals. And finally, number 8, this property is really simply just a combination of 1 and 7 right here. But specifically, think about this case where g of x is a constant function, okay? So, but generally speaking, if f of x is less than some m, this large m, there's this capital M right here, is a bounding maximum value of this function. This function does not get larger than that on the interval of a, b, but it also doesn't get less than the little m. In that case, then the integral of this has to be sandwiched in between the integral of this constant function and this constant function. But if you look at this, the integral of these constant functions is defined by this. So specifically, and this is another property that we need moving forward to prove some important properties, but then this integral right here of the function f of x on AB must be sandwiched in between big M times the length of the integral and little m times the length of the integral.